Today, we'll be talking about the electron cloud. Please get out your notes and the periodic table. Electrons are found outside of the nucleus, in a region of space called the electron cloud. Electrons are organized in energy levels of positive integer value. These energy levels correspond with the period numbers on the periodic table. For example, if I was talking about energy level 1, that would correspond to the first period number on your periodic table. Energy level 2, energy level 3. It is convenient that these period numbers are already labeled for you. Within each energy level are sublevels, designated by a letter S, P, D, or F. These are represented by the blocks on the periodic table. These blocks are color-coded for you on this periodic table right here. As you can see, the S block is outlined in red, which includes the helium. The P block is outlined in green. The D block is in blue, right in the middle. And then you have the F block, which is outlined in yellow. Now, it is important for you to note which energy level these blocks start at. So for the S block, it starts at 1s, energy level 1. For P block, it starts at energy level 2, so we write 2p. For D block, it starts at energy level 3, so 3d. And then F block, it starts at energy level 4, so 4f. Please take a moment, pause the video, and make sure that you have labeled your periodic table according to this. Each sublevel corresponds to a certain electron cloud shape called an atomic orbital. I have an analogy that can hopefully help you with remembering the different parts of the electron cloud. Think of the entire electron cloud like Tompkins High School. The energy levels are like the floors in the school. The sublevels are like the teacher's rooms on a floor in the school. The orbitals are like lab tables within a room. The electrons are like people sitting at a lab table. This gives us a good prediction of where the electrons are located. What do the atomic orbitals look like? Well, they have a complex 3D shape. Luckily, you will not have to remember them. The s orbital looks like a sphere. The p orbitals have 3 different orientations, and it looks kind of like a figure 8. How are they organized around the nucleus? They are 3D region around the nucleus. Orbitals tell us where there is a high probability of finding an electron. Here is a picture of the orbitals that make up the first 4 sublevels. This is an important rule to notice. Each orbital can only hold a maximum of 2 electrons. Let's look at an s sublevel. For an s block, it is 2 element wide. This means that the s sublevel only has 1 orbital, because it can only contain 2 electrons. Therefore, how many total electrons can fit in S sublevel? That would be 2. Now, remember that for every 2 electrons, I can count off an orbital. Let's look at the p sublevel. 1, 2, so that's my first orbital. 1, 2, that's my second orbital. That's my third orbital. Therefore, a p sublevel contains 3 orbitals. How many total electrons can fit in a p sublevel? 6. That would be my answer. The d sublevel has 1 orbital, 2, 3, 4, 5. How many total electrons can fit in a d sublevel? Well, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then lastly, I have an f sublevel. 1, 2, 3, 4, 5, 6, 7. It's got 7 orbitals. How many total electrons can fit? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Electron configuration and orbital diagrams. There are 3 rules that can govern the filling of an atomic orbital. The first is Aufbau principle. The second is Pauli exclusion. And third is called Hund's rule. The Aufbau principle. It comes from the German verb to build up. The principle states that electrons enter orbitals of lowest energy first. And when you look at your periodic table, that would be energy level 1. The alpha order lists the orbitals from lowest to highest energy. I understand that this looks very complicated right now, but I promise we will teach you how to read this off of the periodic table. You do not have to memorize this. What do these letters and numbers mean? Well, it is color-coded for you, but the first number represents the energy level. The letter represents the type of sublevel, so you have choices between S, P, D, and F. The superscript represents the max number of electrons. Remember, you will learn to use the periodic table to determine the alpha order. It is not to be memorized. The Pauli exclusion principle. An atomic orbital may hold at most 2 electrons, and they must have opposite spins, called pair spins. What does this look like? Well, an orbital is typically represented by a square or just a single line. Electron with a spin, it either goes up or down. This is an example of 2 electrons within the same orbital. Remember, an orbital can hold out to a maximum of 2 electrons. These electrons are called paired spins because they will spin in opposite direction. Our third is Hund's rule. It states that when electrons occupy orbitals of equal energy, such as 3p orbitals, 1 electron enters each orbital until all of the orbitals contain 1 electron with spins parallel. Basically, according to Hund's rule, electrons prefer to be in their own orbital. Therefore, if we have 2p3, the first electron is going to go here, the second electron is going to occupy its own orbital, and the third electron will occupy its own orbital. However, if we have 2p5, then second electrons then add to each orbital so that their spins are paired with the first electron in the orbital. So that means for 2p5, the first electron will be in its own orbital, second will take up its own, third will take up its own. Fourth would have no choice but to be with the first, and fifth would have no choice but to fill up this orbital. But when they fill up, they will spin opposite to the one that was already there. Let's do some examples of electron configurations. An electron configuration will use the alpha order to show how electrons are distributed within the atomic orbitals. Let's start with carbon. It is element number 6 on the periodic table. If the atomic number is 6, it should have 6 electrons, according to 8. Our electron configuration will have to account for all 6 of these electrons. Let's start with the lowest energy level, that is number 1. We have to go to the S block, and it contains 1, 2 electrons. So we would write 1 as 2. Remember, the 1 represents energy level, S represents the block, and 2 represents the number of electrons. Next, we go down to the second energy level, so 2. We're still at the S block, so 2s, and now we count 1, 2 again. We have 2 electrons, and then you have to go across from there to reach the P. The P block is still starting at the second energy level. Now you have to count how many electrons you have to go in order to reach carbon, and that's 1, 2. So that's it in terms of electron configuration for carbon. Now let's check if we have accounted for all the electrons in carbon. All you have to do is add up the superscript in the electron configuration you just wrote. 2 plus 2 plus 2 is equal to 6. Fluorine is element number 9 on the periodic table. It has a total of 9 electrons. It will go through the exact same steps that carbon did, just a little further. So 1s2, 2s2, 2p. Now we have to count. So we are at the P block, second energy level. It's going to go just a little bit further than carbon. So 1, 2, 3, 4, 5. And I stop there because I have reached fluorine. And finally, that's its electron configuration. Once again, let's check the superscript to see if we have accounted for all 9 of the electrons. 2 plus 2 plus 5 is equal to 9. Now I want you to pause the video and try magnesium and argon on your own. Welcome back. Hopefully you have figured out the electron configurations for magnesium and argon. Here you can check your answer. It is important for you to remember how to read a segment of the electron configuration. Remember that the big number in front is the energy level. that corresponds with the period number on your period table. The letter represents the sublevel, or the block that you are in. The superscripts represent the number of electrons. Now we are going to go from the electron configuration to figure out the elements that it represents. All you have to look at is the ending of the electron configuration. In this case, we end with 3d3. Note that the D block starts one off from the period number. Therefore, we are at 3D and we have to go 3 times. 1, 2, 3. The element name is vanadium. Let's do that again. The ending for this electron configuration is at 4d9. For the electron configuration above, we started with energy level 3 for D block. Now, since we're starting with 4d9, we must be here, and that is 1, 2, 3, 4, 5, 6, 7, 8, 9, and our element is Ag, or silver. Let's look at the last one. The ending for this configuration is 3p6. We are looking at the third energy level, and the P block, which is all the way here, and we are counting 1, 2, 3, 4, 5, 6. And our element is argon. We are going to skip orbital diagrams in your notes for now. It will be mentioned in a later video. Let's talk about noble gas configuration. Some elements have large numbers of electrons, making their electron configurations cumbersome to write out in full. The noble gas configuration was developed for use with larger elements as a shorthand way of writing electron configurations. We are going to use the noble gases in group 18 to help us with this. Before we demonstrate how noble gas configuration work, I want you to pause the video and make sure that your own periodic table looks as nice as this one right here. You should have all 4 blocks labeled, and I would suggest that on the side, just like I've done here, you label the energy level for each of them. Make sure you label this, it will help you a lot. Also, recognize where your noble gases are. Let's start with our example, strontium, which is element number 38 on the periodic table. It has a very long electron configuration in order to account for 38 electrons. So now let's see how we're going to find the noble gas for it. All you do is go from strontium, I'm going to draw on this periodic table so to show you, all the way to the right, and you're going to go up 1. And that is the noble gas you're going to use. In this case, that would be krypton. So I would write krypton in the bracket. And now from krypton, let's see how many more electrons I have to go to get to strontium. You go 1, 2, and that's it. And those are in the 5th energy level in the S block, and there are 2 of them. And that is it. And you can check. The 5s2 matches the ending to the full electron configuration. That means from 1s2 all the way to 4p6 was taken care of by the krypton. Okay, let's try another one. Let's try manganese, element number 25 on the periodic table. So once again, I'm going all the way to the right and up 1 to find my noble gas, and that would be argon. And what else do I have to account for? Well, the 2 electrons in the 4s and 1, 2, 3, 4, 5 in the 3d. 3d5. And once again, you can check. This is the ending to the full configuration that matches. And then all the way from 1s2 to 3p6 was taken care of by argon. All right, now let's go to our most extreme example of this, which is bismuth. Element number 83. Okay, without noble gas configuration, imagine you would have to write this entire thing out. Okay, so from bismuth, I'm going to go all the way to the right, up 1. I found my noble gas, and that is xenon. Okay, and then I have to account for 1, 2 in the 6s. And this is where it gets tricky. Do you see how this F block is coming out of the periodic table? Well, there's a reason for that, because then the periodic table wouldn't fit on a piece of paper. So they have to kind of make it go down here. Okay, so that means you got to go down, okay, and account for this row first, the 4F. And there are 14 electrons in that 4f. Now you can go back to 5d, and then 1, 2, 3, all the way to 5d10, and then what's left? 6p3. And that's how you end this. And you can check, this is the ending to the full configuration right here. But you save yourself this entire part, which was taken care of by writing xenon in that bracket. That's it for the video today. Please take care of the corresponding homework that is linked above this video.